Morning, ladies and gentlemen. Project has gotten going as usual. The servers haven't. So we have pushed the homework deadline till today. We thought we'd sorted this out last spring because last spring it was run with 500 people, but it was, well, maybe 450, but it persists, and, well, there it is. So apologies for that, but I would like to say it's back now, except I know that it has deliberately been taken down. Read the last blurb. If you don't know what that is, Google it. It's copy on write, some kind of Linux malware problem, and we have to protect ourselves from all of this. So at the moment, or sometime during the lecture, it's going to be taken down and brought back up, I think also during the lecture. We will give you only a short homework because you're working on a project. So there may be some problems that are there on the homework, but we'll say you don't have to turn these in, right? So that you have them for practice if you want. But the number that you have to turn is going to be relatively small. Do you have any administrative questions? There is an administrative deadline today. Yes? Pass, not pass, something or other? Anybody, anything? This is the, yes? The question is, are the grades curved at the end of the semester? They're not. That's what we advertise. Because we want to give ourselves the option of everybody getting good grades if everybody does well. So Berkeley has a curve. There are many classes that are curved with X% get A's and X% get B's. We're not like that. The grades in this class tend to be very high. I've looked at the scores now. The homework scores are on B courses, the midterm scores, and the lab scores are up to, and Project 1. And I expect that a significant fraction, at the moment I'm looking at 75% A's and B's. However, if people let up, there's 2 projects still to go and a final exam. If you keep working the way you are working, then I anticipate high grades, as we have given last fall as well as last spring. And those weren't us being generous. I'm not known for being a softie, but the students, they work hard and do well. So we have deliberately not limited ourselves by a curve. More questions? What you're seeing here is self-selection. The people who choose to come to lecture tend to, in general, know what's going on and tend to not be worrying too much about whether they're pass, not passing, or others. It's the others. And so, well, maybe I'll get some emails. We'll see. Okay. I should say, by the way, that how much I appreciate your presence. I said in the beginning of the course, and it's true, and it's still true, it's true in every course. If lectures are any good, it is not the instructor entirely, it is at least half the presence of the students. And that is why when we are asked, I've thought about videoing lectures, but I'm not an actor, so I can't talk to a blue screen and make it look like I'm actually talking to somebody. And the fact that it's artificial just comes out. So you have other things to do. It's rainy, it's Friday, it's almost Halloween, there are parties over the weekend. And that you are here is something that I appreciate very much. Thank you. Okay. Right, back to work. So main business of last time was the main theorem, or certainly one of the main theorems of probability and statistics, the central limit theorem. So a limit theorem is one that operates for large sample sizes. And it says that if you have a large random sample from any population whatsoever, regardless of how awful the population looks like, and you add up the numbers in your sample. Now, why would you do that? Under what circumstance would you be interested in the sum of your random sample? So before taking an average, yes, but before that, why just the sum? Why would you be interested in just the sum? Where did we look just at a sum and not at an average? Yeah. TVD is distribution. So here, what I want you to imagine is there's a population, right, say of incomes, and I'm sampling 200 incomes. So I have a list of 200 numbers, right? Under what circumstance would I be interested in the sum of those 200 numbers? It's not just do I add anything to get my statistic, but that the statistic is the sum of the sample. Under what circumstance? There's one place where we have used this. Where has it been? Actually, two, but really one place where the sum really has mattered. Yeah. Roulette, yes, adding up money, pluses and minuses. Thank you. Sums in gambling games, how much you make in each game, and then you add up the total is the amount of money you make. That's one place. Very good. There's another place which does not look like a sum but actually is, and that's when we've counted the number of items of a certain kind. When we have counted the number of heads in coin tosses or the number of purple plants among the peas. Counting is the same as first coding your objects, 1 for the ones you want to count and 0 for everything else, and then adding up that list of zeros and ones. So counting is a sum. In those two places, the sum is something very natural that you want to study. In most other places, it's the average. And as was just said a little while ago, to take an average, you first have to take a sum and then divide by a constant. It's your sample size. So if you understand sums, you understand averages as well. We know also that proportions are special cases of averages. If your list has been coded zeros and ones, then the proportions of what you're counting is just the average of the zeros and ones. So understanding sums leads to understanding averages, which also includes understanding proportions. And so in more advanced textbooks, you will see the central limit theorem written just in terms of sums. But for us, the most interesting statistics are going to be the sample averages and the sample proportions, so I always throw in average and proportion wherever I can. The point is, no matter what you start with, the distribution of these statistics is roughly normal, and that allows you to do some inference. Now, last time we saw many instances where the statistics came out roughly normal, and you will have recalled that it was quite easy to see where it should be centered. Right? That's a natural expectation. What we want to do today is just look at how the sample mean behaves. So it's a large random sample. You're drawing it from any population. The probability histogram for the sample mean is roughly normal. It's centered where you want it to be centered, at the population mean. Right? So if you are sampling from 75% purple plants and 25% white plants, then in your sample, the histogram of the proportions will be centered somewhere around 0.75 if you're looking at proportions of purple. Now, any normal curve is essentially defined by two quantities. They all look like bells. What you have to do is put the scale down on the horizontal axis. So the center is an important thing, and then what's the other number that allows you to define the scale completely? The standard deviation. Right? Because you know that then the minute you can put the SD, you can put down what that point of inflection is on either side. And the minute you've put down two numbers on the number line, you've put down the entire scale. So to identify this curve completely, you need the SD, and we don't know it yet. So what we're going to do today is we're going to spend some time studying the variability of the sample mean. Now, we notice some things about it. We notice that as the sample size gets larger, the variability gets smaller, right? But how much smaller? Exactly what are we measuring? This is something interesting to look at, and there's a beautiful result that you will see. Okay, so very familiar data set. It's the flight delays that have a mean of about 16.7 minutes. Okay, so there is your histogram. We saw that last time. The that little balance point there is the mean of 16 and a bit. And what we're going to do is we're going to take samples from this, look at the sample means, and see where those sample means land. And then we're going to vary the sample size and see how things change. That's the plan for the next 20 minutes or so. Everyone with me? Okay. So the goal is to try to hone in on this number right here by sampling. So what I'm going to want to do is something we've done before. We're going to take samples, compute the mean, and then see where those means land. We've done this over and over again. We are going to want to change the sample size. So what I did was I took our code that we had before and just collapsed it all into a function that we can call. And the function is called simulate sample mean. It takes the name of a table, the label of the column containing the variable, the sample size, which we are going to vary, and the number of repetitions. Today, just for comparability, I have kept the number of repetitions at 10,000 for every single thing that I've done. But you are welcome to vary it. The more repetitions you have, the closer you get to the actual probability histogram. So what we're going to do is, for a given sample size, we are going to do these many repetitions, many simulations. We are going to draw a sample of that sample size, calculate the mean of the sample, and then collect all the means in an array. And then we create a table with all these means. And now I want to scroll. Actually, I'll stop right there. Questions about any of that? Please note that we're still sitting inside a def statement. So all of these names like table, label, sample size, etc., they have an existence only in this cell. They're part of the definition. When we use them, we will put in the name of our table and our column and so on. Okay, thus those lines. Questions? Seem familiar? Yes? Okay. The rest of the lines are all sort of display diagrams and print statements which you can blithely ignore. I'm not going to ask you to do printing. However, they will be there in your textbook. See this collect, draw a histogram, label the axes, print this, that, and the other. We'll see. Okay, so I'm going to run simulate sample mean. The table is called delay because I just selected the delay column. I didn't want to carry around a big table. The table is called delay. The column label is delay. Sample size, I'm going to start with 100, and I'm going to do 10,000 repetitions. These are my code, which you can ignore, for setting all the scales of all the histograms that we draw to be exactly the same, so you can visually compare what is going on. Okay, here we go. 10,000 repetitions of a sample of size 100, taking the mean, and we end up with that. So there is a bunch of stuff to notice. Because it didn't take long, I'm going to answer a question that some people have asked me, which is, what is this semicolon? Because there's never been a semicolon at the end of anything, yet they keep popping up. I'm going to run the cell without the semicolon, and you'll see why it's there. It's because of this. It talks to me. It tells me stuff I don't want to hear. I already told it that I want these to be the limits, and so the semicolon is just to get it to shut up. That's all it does. So if you don't have that, sometimes you get a matplotlib, long string, and it messes up your screen. So that's all that does. This is just X is going to go from 5 to 35. That is. Don't worry about that. So the first thing I want you to notice, sample size 100. Yes? You have the mean of a sample of size 100. It's kind of trying to look normal, but it isn't quite. You agree? You're sampling from something very skewed, and what you're saying is that 100 isn't quite enough to get to normality. What we'll do is we'll run some larger sample sizes, and then we will look at all of these numbers here. So play the same game with 400. So 10,000 repetitions of a sample of size 400, and now it's a little more normal-like, though I can still see a tad of skewness to the right-hand side. And if we play again, 625, some of you will have noticed that I am using perfect squares as my sample size. There's a reason for that. Much better. So what we're seeing is that as you increase the sample size, the approximation by the normal gets better. But now what I'd like to do is I would like to look at the numbers, exactly where is the center and what is the spread of this curve. So for that, we're going to go back to sample size 100. So sample size 100, the population mean is just 16 2/3 roughly. Okay. There are 10,000 sample means in this picture. Those 10,000 numbers have an average. That's the balance point of this histogram. That number is 16.66 something, not so far from your population average. Right? So if you just look at those two lines and convince yourself that when you draw a sample of size 100 and take the sample mean, you kind of expect it to be around the population mean. And I want to check that the same thing happened with a sample of size 400. The population mean, of course, is the same. It's the same population. And the center of this, the balance point of this curve, is very close to the population mean. You compare this number, that's the population mean, and this is where your curve is centered. Good? So what you are learning is that there's a term we used some time ago, unbiased. What you're learning is that the sample mean is unbiased. It's an unbiased estimator. It's not typically always on the right-hand side or always on the left-hand side. It gets the answer right on average. And when you go to a sample of size 625, you still have that same closeness that you see. Okay? So we're good for the center. We understand the center. If you draw a sample and look at its mean, you expect that to be just around the population mean. And now we have to define around. And you will recall that the SD of any normal curve is the distance from the center to the point of inflection. Yep. So physically, there is some notion of width of a curve. And now I want to go back and I want to look at the population SD, which we saw last time was about 40. And now I'll compare with the SD of these guys. First, look at the scale. This one's 40 and this one's 4. You agree? So the sample means are very tightly clustered. And before we get into exactly what the numbers are, let's go back to this histogram. This is the distribution which is widely spread out. The SD of the entire distribution is 40. What we're trying to get at is this number right here. And our sample means are very tightly clustered just around here. It's clear what's going on? And so even with a sample size of 100, which is not huge in this context, the sample means are very tightly clustered. It's essentially population mean plus or minus about 4. Maybe plus or minus 8, plus or minus 12 at the most. Okay, so now I want you to look at this number. This was about 40, and this is about 4. Yes? Sample size is about 100, so you agree we dropped the SD by 1/10? All okay? All right, so now let's see what happens when we sample 400. A population SD is still 40. This is about 2. Yep. Dropped by 1 in 20. 40 divided by 20 equals 2. Yep. Relation between 10 and 100. There are lots of relations between 10 and 100, but I'm looking at 10 and 100. 20 and 400, what's the relation? Square root. 10 is the square root of 100. 20 is the square root of 400. So with 625, what do you expect will have happened to the SD? You really want it to be 1 in 25, right? It's one of your 4th or 5th grade complete this pattern questions that you got on your worksheet, right? So you really want the next SD to be this thing, to be 40 divided by, what's the square root of 625? 25. So if I take 40 and I divide by 25, what do I get? Okay. 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 That's what I have to do? Yes? All right. How'd you like that? This is how theorems are discovered. You're noticing something. Every time the SD of that normal curve is the population SD divided by the square root of the sample size. And maybe it's just these sample sizes, whatever we can see. So of course, we've got a computer which is going to do this for every possible sample size. This thing takes a while to run, so I am going to run it, and while it's chugging, I'm going to talk to you. Okay. So I want to observe a few things. First, we can see that as the sample size is increasing, the sample means are getting more and more tightly clustered about the population mean. That is consistent with the SDs of these curves having the sample size in the denominator. Population SD divided by square root of sample size. Notice, divided by, something to do with the sample size. As the sample size increases, that SD decreases. SD decreases, the variability decreases, your accuracy increases. Yep? The accuracy increases, but slower than the sample size. The sample size is just going up. But what's affecting your accuracy is not the sample size itself, but the square root of the sample size, which is a smaller number. And we'll see in a bit how that affects anything. Am I still chugging here? No, we're done. Okay. Let me show you what that simulation does. So we did 3 sample sizes. We did a sample size of 100, 400, and 625. Of course, we could have played that game for any number of sample sizes. You agree? So that's what this simulation has done. It has taken a sample size of 25, very modest. It has simulated 10,000 sample means, just as we did for our other sample sizes, and figured out the SD of that curve. And it has figured out also our guess. The population SD divided by square root of 25. That's what it's done there. And then it's done a sample of size for samples of size 50, so 10,000 samples of size 50, 10,000 samples of size 75. Once again, 10,000 samples of size 100, even though we'd done that before. Okay. So before we start looking at numbers, could you please look at that table and just make sure that you understand what is represented in each one. Let me actually ask you some questions to make sure that we're all with us. Is there a simulation in that first column? No. Where did those numbers come from? My head. That's where those numbers came from. Okay. Here. Is there a simulation in this column? You bet. That's what took all the time. For every single row, there is a fixed sample size. We chose 10,000 samples of that size, computed the 10,000 means, drew that histogram, and found the SD of those 10,000 numbers. And we did it for every single sample size from 25 to 625 in increments of 25. So 25, 50, 75, 100, etc., up to 625. So this is where all the time was taken. What's this? Any simulation there? No simulation. That's the formula that we guessed. We guessed that these numbers ought to be the population SD divided by the square root of the sample size. So we simply compute that number, like we did 40 divided by 25, right? So this is just 40 divided by whatever, and not exactly 40, 39 point whatever, divided by the square root of the sample size. So there's no simulation here. This is just a quick calculation. And now we're going to look at this number and this one. Please compare column index 1 and column index 2.
So like for fun,
So that's an interesting question. Can you hypothesis test a theorem? Okay, so first I will say the central limit theorem isn't giving you the SD. The central limit theorem is giving you the normal shape. All right, so that's not what we're talking about. It is a very interesting question as to whether you can hypothesis test a theorem. The SD is an easier calculation. People who are in Stat 88 are seeing it somewhere. I certainly wrote it out for them. I think if you are going to, you can verify a theorem by simulation. That's what we're doing, right? I am not yet comfortable with, if the theorem were true, then such and such result would happen, but such and such result isn't happening. Mathematics isn't yet being tested like that, but maybe. The thing is, with mathematics, you want to go from step 1 to step 2 to step 3 to the end and know that everyone is correct. So there shouldn't be a need for a hypothesis. If, however, you have an unproven theorem, right, which is a hypothesis, so somebody's conjecture, then you could have a go. Then you could certainly have a go. That would be fun. Yep. But CLT is not a conjecture. By the way, to actually get a proof of the CLT, an honest-to-goodness complete proof, the first place I know of it in this university is the first-year PhD program. It's deep. There's stuff going on there. Okay. Enough distraction. What we have seen is that this column looks like this one, yes? Sure, looks like we have a theorem. Why don't we visualize? I'm just going to plot against the sample size this column and this one. There are really, truly 2 plots there. There is a blue plot, which is the results of our simulations, the SDs we got from our simulations, and there is a gold plot that is our guess of formula. They are sitting right on top of each other. That is what a theorem looks like. And so now we have a pretty good understanding of the variability of the sample mean. Okay. Fix a sample size that is large. Or I should have said large here. I'm just assuming that we're working in the large sample setting. Draw all possible random samples, take the mean of each sample, you'll get a whole lot of means. We've been taking 10,000 means. These things will be roughly normal, centered at the population mean with an SD that we can now write down. And so I will stop for a second, and I will take questions on this slide, and then we will see this observation. What does it tell us about the accuracy of the sample mean? Questions yet? Yes? Remember, so the question is, what does a central limit theorem predict if the sample size is close to the population size? Remember that all our samples are drawn with replacement. So even if you have a population of size 3, you'll be drawing 3 million times, that's fine. If the sample size is close to the population size, then without replacement sampling doesn't look like with replacement sampling, and this doesn't apply. But it does apply in the typical situation in data science where you've got a massive grade population and your sample is big, but it's still small relative to the population. Okay. All right, so I want to look here. This is population SD divided by square root of sample size. So let's make a few observations. Accuracy. Small SD, high accuracy. This is the typical use of the word accuracy. Okay? So we say as the sample size increases, the sample mean becomes more accurate. More accurate for doing what? For guessing the population mean. It just hones in on that little balance point that we had in our original histogram. Okay, so sample size increases, the accuracy increases. There's something missing, actually, and given that you brought up the issue of the population size, notice that the population size is completely missing from this measure of SD. Whether you are sampling from a population of size 3 or 30 or 300 billion, that is the same formula. Why is that? Why is that not weird? because you're sampling at random how? With replacement. And therefore, all that matters are the proportions in the population, not how many there are. Right? So if you have a box of 10 million zeros and 10 million ones, and you sample with replacement each time, the chance of getting a 1 is 50%. You agree? That is the same as sampling from a box that has 1 0 and 1 1. So it's only the proportions in the population that matter, not the population size. And that is why polls worth very small percents of the population, 1% of the population and so on, are accurate enough that TV news anchors are, going up, before the polls have closed, starting to make projections based on very small random samples. Small in the sense that they are small percent of the voting population, but when the voting population is in the millions, then even 1% of the voting population is quite a large sample. And when you put square root of that in the denominator, your SD shrinks. So let's collect some of these. Accuracy is greater. Doesn't depend on sample size. Accuracy increases. Okay, now, let me go back to our formula here. Notice that it's not the sample size in the denominator, but the square root of the sample size. So if I want 3 times the accuracy, I need to increase my sample size. Agreed? A natural guess for how much to increase by is 3 times. If you put 3 times the sample size here, is this whole thing going to drop by 3? You have a little problem with the square root. It's going to drop by the square root of 3. Yeah? That factor is going to be inside the square root and get, so it's going to drop. So if you want 3 times the accuracy, what do you have to multiply your sample size by? 3 squared. You have to multiply it by 9 so that when you take the square root, you get a 3 back. Yes? If you want 10 times the accuracy, what do you have to do to the sample size? Multiply by 100. Yes, so please note, accuracy doesn't come cheap. You have to really increase the sample size because of this dampening factor of the square root. And that is called the square root law. If you multiply a sample size by a factor, then the accuracy goes up by the square root of that factor. So if I multiply the sample size by 5, I don't get 5 times the accuracy. I get square root of 5 times the accuracy. And this observation can be used to do something very important. All along, we have been doing inferences based on samples, and somebody has drawn the sample. Or we have chosen to draw a sample of size 400 or 625, or we got a sample of 1,174 mother-baby pairs. Somebody handed us a sample. But that person designed their study, and they designed their study based on their resources and the accuracy that they were willing to accept. And based on that, they chose a sample size. Now, if you as a data scientist don't come in after the sample has been drawn, but you are called in before to advise on how big of a sample should we take to get a certain desired level of accuracy, then what are you going to do? Then you're going to see, well, how are we measuring accuracy? We're measuring accuracy by these SDs. If we are looking at a sample mean or a sample proportion, we actually know how to calculate that SD, so maybe we can use this to find the sample size. So let me just say what we're about to do now compared to what we've been doing thus far. Thus far, we have had a sample of a particular size, and we have computed the SD of our estimates. So we've taken the population SD, we've divided by the square root of sample size, we've got a measure of the accuracy. Now what we're going to do is we're going to say, okay, we want our estimate to be this accurate. How big of a sample should we take? In other words, we are going to more or less tell ourselves the SD and ask ourselves, how big of a sample should we take? Do you see that it should be possible? Provided you know something about that population SD, it should be possible. Okay? So there is one situation in which it is clearly possible. Actually, let me talk about the situation first. Okay. So what we're going to do is something topical. We're going to try and estimate the percent of candidates, percent of voters that are going to vote for a particular candidate. So we are in the setting now of zeros and ones. Every voter is labeled a 1 or a 0, depending on whether they are going to vote for candidate A or not. And we are going to estimate the percent of ones in our population. So imagine a population of millions of voters. You're going to take a sample and you're going to estimate the percent of ones in it. You've got to do something to get this percentage. How do you estimate an unknown number in a population? You take a random sample and then? So your random sample will give you one proportion. Now what? Bootstrap it. Get a confidence interval. We know how to estimate. We get confidence intervals. So we are going to construct a confidence interval, and we want this thing to be accurate, so we want a narrow one, and we're going to specify how narrow. And that is really up to the scientist or the whoever is doing the study to decide how much accuracy they want. And our question is, how big should the sample be if we specify the accuracy? So what we're going to do is we're going to take a look at a 95% confidence interval for the population percent. And we're just going to see from left to right, how wide is it? Could somebody remind me how we do a 95% confidence interval? So we've got our original sample, right? It's a bunch of ones and zeros. Then what do we do? Terrific. We take the 2.5th percentile and the 97.5th percentile of what? All the proportions that we got. Yes? How did we get all those many proportions? We bootstrapped our original sample. Yes? So by bootstrapping our original sample, we know how to calculate a confidence interval. Problem. What's the problem? We don't have a sample. We don't know the sample size. Yep? We don't have any data. We've got nothing to bootstrap from. This is why we have theory. What is the central limit theorem telling you about that distribution that we can't get because we don't have a sample? What's its shape? Normal. And it's going to be centered where you want it to be centered. Yep? And now there's a plus or minus. If you want to pick up the middle 95% of a normal-like distribution, you can do either what we have done thus far, which is go 2.5th percentile and 97.5th percentile, or the middle 95% of a normal curve. How do you get that? Center plus or minus 2 SDs. Yep? So, center, 2 SDs this way, 2 SDs that way. How many SDs total? 4 SDs is the width of your 95% confidence interval. Right? Do we know what an SD is? Yes, we now have a formula. So we're kind of in shape. We can do this thing. All right, so we've got our confidence interval is going to be center plus or minus 2 SDs of the sample proportion. Remember that the proportion is a mean. We can use our formula. And so 2 SDs of sample proportion on both sides of the center. And so your total width is 4 SDs of the sample proportion. Nicer. Okay, take a look at that. Last line. Width of my 95% confidence interval is 4 lots of the SD. Agree or disagree? Yes? Are we sure? What would the width of, yes? No, it's coming from the fact that it's normal. The central limit theorem says that the proportions are going to be normal, right? And we checked last time that for a normal curve, center plus or minus 2 SDs gives you 95%. Right? That's approximately 95%. The bounds that we had for generic distributions said at least 75%. That would be true no matter what the shape was, but the central limit theorem is telling us we know the shape, right? And it's a well-known shape, well-studied, and for that shape, it's 95%. More questions? Yes?
How does the 95% confidence interval take the place of like the population SD that was in the previous formula?
There's a population SD right here. So this is the same formula. So could you take a look at this line? The previous formula said SD of population divided by square root of sample size. Yes? Our population now is zeros and ones. Because I want the total width of the interval. That's the discussion right now. We are looking at the left end of the interval to the right end of the interval. How many SDs is that? Well, from the center to one end is 2. From the center to the other end is 2. So from left to right is 4. Okay? So let me ask another question. 68% confidence interval. For 68% on the normal curve, you have to go center plus or minus what? I'm sorry? 1 SD on either side. So from left to right of that interval, how many SDs would you have? 2 SDs. Right? For 95% confidence interval, it's going to be a wider interval, and it's going to be 4 SDs from left to right. That's the 4. Right? You can think of that as 2 times 2. The previous one was 2 times 1 for 68% confidence. Okay, so the width of the interval is 4 times the SD. And so now we have to figure out what accuracy we want, and that is something that's going to come down from us from whoever wants us to do this study for them. And so supposing they say, well, I'm okay with the total width being 3%. I'll take 3%, but I won't take any more. Right? For some reason, they came up with 3%. In your text, I do it with a different percent. Okay. So from left to right, they're willing to have a 3% difference. So then what you have to do, then you have a little inequality. This 0.03 is your 3% written as a proportion. And this is what we said was going to be the width of the interval. 4 SDs for the proportion. Any questions about that line? So there's a bunch of stuff here that we are known, some things that's unknown. Let's just look at all the bits. This is where you're seeing the 95%. It's hidden. This is 2 times 2 SDs on either side. That's the 95%. That's the 4. This whole thing from here to here is the SD of the sample proportion. And that is the amount of accuracy that we're willing to tolerate, or the amount of spread that we're willing to tolerate. Okay. All right, so now I want to go through and one by one look at which of these numbers we know and which we are trying to find. This one, 4, everybody knows what 4 is. SD of the 0-1 population, we do not know. That is exactly our problem, right? That population is some unknown proportion of ones and unknown proportions of zeros. That is a great, big, huge question mark right now. We do not know that. The sample size we're trying to find. Don't know that either. 0.03, everybody knows what 0.03 is. So if we're trying to find the sample size, the thing that we need a handle on is this guy, because if we just turn this inequality around, your sample size can be written in terms of the 4, the 0.03, and this unknown SD. Yep. So if we could somehow get a handle or at least a bound on that unknown SD, we'd be in good shape. So what I'd like you to do is just really convince yourself that you agree that this line is the same as this line. We've just multiplied and divided on both sides by the square root of the sample size, and then also by 0.03. It's a little eliminate the variable move. Okay, so go try it out on pencil and paper and see that it works. Okay, so the thing that we need to do is to get a grip on this thing right here. The SD of a 0-1 population. So what I want you to imagine is a 0-1 histogram. How many bars does it have? 2. The possible values are 0 and 1. So there is a bar centered at 0 and there is a bar centered at 1. Yep. And they could be, one can be taller than the other depending on what is the proportion of zeros and ones, but the minute you know one of them, you know the other. The other one is 100% minus the one you know. All clear? So what I'm going to do is I'm going to show you. No. I'm going to show you a pair of such histograms. The blue histogram is when the proportion of ones is 1/2. Right? So then you have two equal bars, one at 0, one at 1. Right? So it looks like one big block, but there's really a bar at 0 and a bar at 1, the blue histogram. Is it clear what that blue histogram is? Yep. The gold histogram, what I've done is I've taken 90% ones and 10% zeros. So you can take a look at those and agree that those two are 2, 0, 1 histograms. Of course, you can imagine any other percent. You can take 73% ones and the rest zeros. You can take 5% ones and 95% zeros. You can do anything. I just want to look at these two and try to compare the SD without doing any calculation whatsoever. So remember, what does an SD measure? Distance, yes, from the mean, from the center. Okay, so we're going to look at the blue histogram. Half zeros and half ones, no surprise that the mean is 0.5. Yes, 0 plus 1 divided by 2, that's what you're getting. Half zeros and half 1. Okay. So that one is how far off from the mean? The 0 is how far off from the mean? Minus 0.5. 0 minus 0.5 is the deviation. This number 1 is how far off the mean? Plus 0.5. Yes? So every deviation is either minus 0.5 or plus 0.5. You have equal proportions of minus 0.5s and plus 0.5s. What's the standard deviation going to be? The standard deviation measures the rough size of the deviations without the sign. Yes? You square it and then you square root. When you square these things, what are you going to get? For every single one, you're going to get 0.5 squared. Right? Some deviations are minus 0.5, some deviations are plus 0.5. Every single one of them, when you square, you are going to get 0.5 squared. Yep? Take the average, you're going to get 0.5 squared. The SD is going to be 0.5. These deviations are roughly, not almost exactly, 0.5 in size. Okay, but what happens when you do this? So what you're doing here is you're taking this total proportion of 100% and you're just piling it all up at 1. You see what happened to the average? The average moved close to 1 because all of the weight, almost all of the weight, is being put at 1. Where are the deviations? 1 is a value, there's the average, that's a tiny little deviation. Yep? How big is that deviation? The average is 0.9, the proportion, yes? The value is 1, what's the deviation? 0.1, that's very small. And 90% of them are like that. 10% of them are larger, but what you're doing is you are taking all of the mass and you're squishing it at 1. What's going to happen to the spread? If you put all the mass in one place, you do all the probability in one place, what happens to the spread in the distribution? So let's take an extreme case. Supposing I took 100% of the probability and I stuck it all at 1. Every single value was 1. What would the spread be? No spread. 0. Okay? So now I take 99 ones and 1 0. Then I'm going to get some spread. Yes? But it's going to be pretty small. The more you squish all the values in one place, the smaller your spread becomes. And so the gold histogram has a smaller spread than this blue fair coin histogram. And indeed, any other proportion will also give you a smaller SD than the 0.5, 0.51. The fair coin is the most variable. So you can try either by simulation or by writing out numbers and calculating the SD, check that it's this histogram, the blue one, that has the largest of all SDs among 0-1 histograms. It's the hardest to predict how that one's going to come out. And if that's the case, then you're home free. This was where we said we were. The sample size had to be greater than something involving the SD of the 0-1 population. The SD, this SD, is at most the SD we got in the gold histogram, in the blue histogram, and that was 0.5. So that SD is 0.5 or less, so safe to take your sample size. Just replace this by 0.5. Safe to take this SD as 0.5. You will not suffer if you do that. And so then you get